Hello, hello. My name is Ted Venema, and I am one of the instructors for your 110 Acoustics course. This is a very important course in the HIP or HIS program, Hearing Instrument Sciences programs over at OTC. It's one of the fundamental courses of your program. In this course, it's when you learn about sound waves, decibels, all kinds of things about sound, because you're going to be dealing with hearing loss. And when you're dealing with hearing loss, you got to deal with sound, because sound is what's coming into people's hearing aids. And sound is what's amplified. Hey, I see a face now. There we go. Can you see me? I'm wondering if you can. Not sure if you can, but it doesn't matter. It's all good. So, anyway. So now we have two joiners here with us. Now I'm going to read to you an email that I sent out on January the 8th, a week ago, and I also just sent it out again this morning, just in case anybody, wants to review it. It's a very important step-by-step email, and it regards kind of the way this course and also your 120 anatomy course is run. And I'm not sure if you're taking the anatomy course at the same time or not. It just depends. But here we go. Okay. So I'll read this to you. Hello, my name is Ted Venema, and I'm one of the instructors for the 110 Bioacoustics course. The name of this course is actually going to be changed to Bioacoustics. It sounds a little bit less threatening than acoustics and psychoacoustics, but at any rate, here goes. Here are some things I want to tell you as we begin the course. The same things are also listed under announcements in Canvas too. I sent out the same email a week ago on January the 8th. If you've already seen that one, no worries. All right, and I'm just reading to you from this weird piece of paper I've got printed up in front of me, okay? Number one, you'll see in Canvas that the course is divided into 6 or 7 units. Each unit takes about 2 weeks to do. Now we'll take 3 weeks for this unit because today is mainly an introduction and I'm kind of going over the layout of the course, okay? Each unit takes about two weeks to complete, and inside each unit, once you open up the unit, you're going to see 2 links. One's in blue and one's in red. Now the blue one is always notes. And usually it's about 3 to 4 pages of notes. And those notes are very, very densely compacted. In other words, they're almost like your cheat sheet from the textbooks. They're like summaries of all the information that you need to know in this course. And whenever I do a Zoom session, I talk from those notes. So it's always really important to have those notes printed up and laying right beside you at your desk, so that while you're watching the Zoom session, you can scratch and scribble and make notes on those notes. Those are yours to download. Don't worry about downloading or printing the PowerPoint slides. That's the red link that you'll see, okay? And that red one, that's got all the PowerPoint slides that I will show you during the Zoom session. And the notes and the PowerPoint slides are tied together. As I talk from the notes, I'm dealing with the PowerPoint, I'm showing the PowerPoint slides. So those are what I'm showing in the Zoom sessions. All right. All right, be sure to print up the notes ahead of time. They're usually about 4 pages in length. Point number 2 here. Each week, I hold a live Zoom session for about an hour in length, and that's this one. That's what we're doing. This is essentially your online classroom. The Zoom session for 110 Acoustics is held every Tuesday at 11:30 Central Time. To watch the Zoom sessions, you have to click on this link. So I'll read it in case you haven't got it. https://otc.zoom, that's ZOOM.us/J/986 999924. There's a link for you. Once you click on that puppy, you'll be able to access the weekly Zoom sessions. In the weekly Zoom sessions, I go over the notes and PowerPoint slides. You must have the printed up notes in front of you while you listen. Take notes on or beside the printed up notes. Scribble on them, underline, highlight, whatever. Those notes are very condensed, but they form the outline, and about 95% of the content of the bioacoustics course is in those notes. You should save the PowerPoint slides as your own file to keep, but you don't need to print up the slides. I will be showing those slides to you as I share my screen during the Zoom session. Point number 4. In case you can't watch the Zoom session at its regular time, not to worry. You might be working, who knows? So I always record the Zoom sessions, so in case you can't watch them live, you can always tune in when it's convenient for you. Here's how to access the recorded Zoom sessions each week. On the same day that I record a Zoom session, I upload it onto the unit as a YouTube video. Once you open up a unit in Canvas, you can scroll down and you'll see the link for the YouTube video, usually near the bottom. Point number 5. Always watch the live or recorded Zoom sessions on a decent-sized computer monitor. Don't watch it on your cell phone because many of the slides will have details on them that can only be seen correctly on a normal-sized computer monitor screen. Point number 6. Feel free to watch the Zoom sessions more than once. Like a movie, when you watch it a second time, you get more out of it. You can also pause the session, stop, and return back to it as well. Remember, the Zoom sessions are only an hour in length. For a course that's got 3 credits, 3 hours of class time is usually required, right? If you were attending college on a normal class and it was a 3-credit class, you probably would have 3 hours of class time. So here, you got 1 hour of class time. That's why I encourage you to watch the Zoom sessions more than once. Okay, if you watch them once, great. And if you get the information, great. But a lot of people think that they get it when they don't. Okay, they'll take a test or they'll take a quiz and they'll say, funny, I got it when you were talking about it, but when you were doing the quiz, I just froze up. The problem is that you didn't make sure that you knew it really, that you made sure you knew it. So it's kind of like absorbing a great big pile of information. I always try to lay it out very carefully. And I lay it out point by point. And in the notes, you're going to see bold-faced headings. Whenever you see the bold-faced heading, that's the content of an area. Make sure you digest that area before moving on to the next area. It's like eating a nice sumptuous dinner. You don't cram the whole plate in your face. You take a forkful at a time, okay? So it's very important to make sure that you really do understand the concept in that section before taking a quiz or a midterm, that kind of stuff. Again, I say that because a lot of people say, oh, I got it while you said it, but when I took the test, I didn't get it. So I'm just mentioning, watch the Zoom sessions more than once. It's really helpful. Last point, number 7. The Zoom sessions are mandatory, and don't let the week go by before watching it. Okay? Don't let things slide for a couple of weeks or you'll really be in trouble. It's all about the Zoom sessions. 95% of your course material is in them. Whether you watch it live or recorded doesn't really matter. The advantage of watching it live is that you can ask a question by talking into your mic. You can ask me a question. Okay? Right now, I see 3 names. I see Alyssa Lloyd, I see Grace Patton, I see Sibby, but I don't see any faces, and the mics are shut off. That's okay. Doesn't matter. Either way, doesn't that may mean you didn't want me to see you or didn't want to have anything to say, which is fine right now. We're just meeting each other. Okay, but pretty soon I'll start the class. I'll start sharing my screen and show you the notes and the PowerPoints that I've been talking about that are in the unit on Canvas. Okay, so we be recording now. We've been talking for probably about 10 minutes. This is just our introduction thing, and this is the first time I've really laid things out in a series of points. But this is an email that I sent out on January the 8th, and I sent it out also again today, just in case, just before I started this particular Zoom session. So, without any further ado, I think I'll start sharing screen, and we'll kind of show you the notes and kind of show you what we're talking about here. First of all, does anybody have any questions? Any questions out there? I see people's mics are off. I see, look at this, I see unmute. What does that mean? I see unmute. I'm going to click that box too. Look at this one. And I see, there we go. I've unmuted people in case they had anything to say. But at any rate, if you do, go ahead and please ask. Otherwise, I'll start slowly into the notes and I'll start slowly showing you the PowerPoint slides, and we'll go on until about 12:30 Central Time, and then I'll stop recording and I'll upload this Zoom session as a YouTube. The YouTube doesn't usually appear until a few hours after, because I have to teach 120 anatomy at around 1:30 Central Time. So then I usually upload the two Zoom sessions, the 110 and the 120. I usually upload those after, in the later afternoon of today. So they usually would appear up around supper time, your time. So are all of you in Central Time in Missouri? I'm not sure if you are. I'll tell you where I'm located. You can see behind me there's a map here. Kind of shows a bit of South America. I'm not there. Where I am is up in the Pacific Northwest. I'm about 90 miles north of Seattle, Washington. I'm in a city called Vancouver, British Columbia, Canada. So I'm talking to you from Canada. Am I a Canadian? Yeah, I'm also an American. My mom was born in Michigan and my dad was born in Iowa. So I've got U.S. in me. I have a U.S. passport and a Canadian passport. I'm a dual citizen. So anyway, but I happen to live here in Canada. I also teach at another hearing instrument sciences program up here in Canada. It's called Douglas College, and it's in Vancouver, and it's a 2-year program just like yours. And it's partly online and partly face-to-face. So it's a little bit more face-to-face than yours is. Yours is a little bit more online. But nonetheless, they take the same acoustics course. They take the same anatomy course. Next semester in the summer, they'll take the same disorders course as you will be. So a lot of the courses are the same. In Canada, we've only got 1/10 of your population. The USA has 350 million people. Canada has 35 million. Yet we're a slightly larger country geographically than you are. But nonetheless, we have 5 HIS programs in Canada. United States only has 3. There's 2 are in Washington State. One's in Seattle, one's in Spokane, Washington, and the other one is OTC, Ozarks Technical Community College in Springfield, Missouri. So I will be coming down to Springfield in early March. In early March, it's the annual Missouri Hearing Society Conference, and this year it's being held in Springfield. So I'll be coming down to Springfield, and I hope maybe I'll be able to meet some of you face-to-face. I'm usually an invited speaker at the MHS, Missouri Hearing Society Conference. MHS is a group of people who are HISs, like you are training to be. They've already done their stuff, and now they're practicing, and they're testing hearing, and they're fitting hearing aids. That's what they do. And that's what you're being trained to do in this program, is become a hearing instrument specialist. So all the hearing instrument specialists in Missouri meet up once a year at a conference where there's speakers and there's lots of swag given out, and there's exhibit halls and of different hearing aid companies showing their stuff, and it's kind of neat. One year, usually one year it's held in St. Louis, the other year it's held in Kansas City, and then it goes to Springfield. It kind of rotates between those three cities in Missouri. So this year, coming up, March 2019, it happens to be in Springfield. Cool, huh? Or as we say in Canada, neat, eh? Okay, what I'm going to do is I will start sharing screen, and I'll show you the notes, and I'll show you some of the PowerPoint that we're going to be looking at here. So, share screen, and here's the notes. Hope you can see them. Acoustics, it says. And then you're going to see all these weird words here. Stuff, sinusoids, frequency, period, wavelength, speed of sound, sound field, resonance, impedance. Well, those are the topics that we will be discussing today, next week, and the week after. So we'll be taking 3 weeks for this particular unit, Unit 1. Excuse me. Now, just below, it says your readings. So your textbook by the authors Lass and Woodford, I believe it's called Hearing Science Fundamentals. Yeah, I think it is. I haven't got my copy here, but you know what it is. It's a nice book, kind of a bluish, soft cover book. Here's your pages that you should be looking at for this particular unit. So pages 2 to 18, 23 to 25, 35 to 36. And in this course, we will cover the physical properties of sound. Okay? Physical properties of sound. Acoustics. Now, if you pluck your nose and say it scientifically, physically, sound is a propagated change in the density of an elastic medium. We'll talk about what that means. Psychological perception of sound is called psychoacoustics. Now, if I stop sharing for a second here and just kind of, we've all maybe heard the old saw, if a tree falls in the woods and nobody's there to hear it, is there a sound? You have to think, well, what is sound? Sound is a propagated change in the density of an elastic medium. Blah, there's a mouthful of words. What it means is sound is caused by a vibration. So as I lean into my drawer here, and I pull out a set of tuning forks, take the elastic band off, and just pick one of these tuning forks. It's a tuning fork. Okay? Now if I ding the tuning fork, it'll make a sound. Okay? So the tines or the forks of the tuning fork are vibrating because I hit it against my hand. And it's making sound waves in the air. As soon as I hit it, it's making sound waves that are floating out through the air. So, are those sound waves occurring if there's nobody to hear it? Sure. So if a tree falls in the woods and makes a sound and there's nobody to hear it, is there a sound? Yep. Because what is sound? A propagated, means it was forced, propagated, change in the density of the molecules in the air. Your air has tiny little molecules. Air is made out of nitrogen, oxygen, whatever. So air has molecules. You can feel them when you wave your hand fast. Their air is a substance. And you're making waves in that substance. Okay? So that's what that long, weird sentence means. So if I share screen again now, and this time if we kind of look toward our PowerPoint slide, you'll see a picture kind of what I'm referring to. So let's go over to here. There. So if you look at that picture, you can see the tuning fork vibrating, and then you can see this pattern of molecules moving. And see how the pattern, sometimes they're squished together, and then sometimes they're spread apart, and sometimes they're squished together, and then they're spread apart. Those are sound waves. Okay? So, does that happen if nobody's there to hear it? Yep. All right. Weird but true. And let's go to the very beginning slide, the very first slide. And you look at this in your PowerPoint. You don't have to have it pulled up. You can always look at it later, but this is exactly the PowerPoint that's on your Unit 1 in red. This is what I'm showing you here. So if you're looking at this PowerPoint here, and I'll make it bigger, okay, you got a whole bunch of words here. And on the very top, you can see a wave. Now this is light waves. Light also has waves, but light is different from sound. Light doesn't need air to go. Light can travel through outer space, and in outer space, there's no air. You see the stars, you see the moon, okay? But there's no air out in outer space, and yet you're seeing the light. So light doesn't need a medium like water or air or steam. Sound does. Sound, if you talk to me in outer space, I wouldn't hear you. Sound has to have molecules to change the movement. Light doesn't need that. Now look at on the left here, AM radio waves, shortwave radio, television, and FM radio, microwaves like you're cooking in your kitchen. Okay, infrared waves, and then finally, ooh, here's our eyes. This is the light waves we can see. And then you get ultraviolet waves, and then you get X-rays and gamma rays. You can see how the light waves get shorter and shorter and shorter. And the light waves we can see with our eyes are here. Okay, that's it. Like a rainbow. This is our visible light. We can see from red up to ultraviolet. And these light waves have certain lengths. And the length determines the frequency. So we're looking at this. We've got a low frequency and a higher frequency of light. That's light. But we're dealing with sound. And sound needs something called a medium to travel through. And a medium, M-E-D-I-U-M, medium just means it needs molecules. Okay, it needs to hit and move molecules. It's got to go through air, or it can go through water. If you had your head underwater and I was underwater and I clicked two rocks together, you'd hear me. Whales talk to each other under the water, so do dolphins. So sound travels through water. Sound also travels through railroad tracks. If you put your ear to a railroad track, you'll hear the train coming quicker. Okay, so sound can travel through air, any gas, can travel through water, can travel through metal. The thing is, all of those things are called mediums. There's something through which the sound travels. Light doesn't need that. Okay, light can travel without that. And light is much faster. You see the lightning way before you hear the thunder. So light travels way faster than sound does. Okay, sound only travels about 766 miles an hour. Did you know that? It's not that fast. The 747 jet flies about 600 miles an hour. So the speed of sound is a little bit faster than a 747 jet with a tailwind. Okay? So sound isn't really all that fast. That's why when you yell across the Grand Canyon, hey, and then you hear, hey, 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 you hear the echo. And that's the sound bouncing off of the wall coming back to you. Okay? The sound takes a little bit of time to travel. Now, it doesn't affect us in speech because, you know, when we're talking to each other, we're pretty close. So anyway, I'll share screen and let's look at our notes again and highlight in our notes what it is that we really should be looking at. Okay, so I'll go back to the notes here and let's scroll down here. So the perception of sound, what's highlighted here, is psychoacoustics. So the first half of this course, up until the midterm, we're going to be covering the physical acoustics, sound waves. What are they? The second half of the course, after your midterm, we'll be covering the perception of sound, the act of hearing. See, your anatomy, the ear, kind of sits between sound waves and the brain. Okay? So the brain is perceiving sound, Okay, and sound waves are coming to your ear. Your ear is a device that helps your brain interpret what sound is. So really, your ear kind of sits between physics of sound and your perception of sound by the brain. So you've got physics of sound, and you have your psychological perception of sound. Enough on that. Simple wave motion in air. We'll just kind of take a look at this. The simple wave motion in air. Brownian motion just means molecules moving around in the air without sound. Okay, so you're not making a sound. It's just the movement of the molecules of the air around you. And molecules, as you know, are tiny little atoms, okay? Everything's made out of atoms and molecules. So molecules are groups of atoms. And molecules are all moving around in the air, just ding, 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 ding. That's called Brownian motion. As soon as you strike a tuning fork, ding, now you've put order in it. Okay, now you've put, all of a sudden now you have a pattern. And that pattern is what I'm showing here in this PowerPoint. Okay? Brownian motion just means there's no ripples here. It would just be the random movement of molecules. And now when I've struck the tuning fork, now I'm making a pattern. And the pattern is squeezing, what it says here, compression, or you could call that condensation. I'll make it closer. You can write down condensation here, same thing, compression or condensed. And here, rarefacted, they're spread out. So here's where it begins, where my cursor is, compression or condensation, rarefaction, compression, rarefaction, compression, those are sound waves. Okay, look at another picture, same thing. The source, and then you've got your condensations, and you have your rarefactions. This picture is showing you the same thing as this picture is, just in a slightly different way. Okay? And then here would be static air pressure. That would just be like Brownian motion, the random movement of molecules in the air without the sound wave happening. So here's something important. Your first concept to really internalize and take home with you, okay? It is this. Look at the C and the R. Condensation, rarefaction. Condensation, rarefaction. We draw those like sound waves going up and down. See my cursor? We draw it like that. But sound waves don't really go up and down. If sound up and down, you and I would be listening like this. Okay? They don't. We draw sound waves like they're going up and down because it's easier than drawing this. If I share screen, let's see, where am I here? It's easier than drawing with this black bar and this white bar and this black bar and this white bar. Okay? So when we draw sound waves, the up represents condensation of molecules. The down represents rarefaction of molecules. Okay? But that's what sound waves are. Sound waves are the top panel here, but we draw them like a wave. All right, that's very important to know. Because in your notes now, if I go escape here, click the screen and hit escape. Your notes, see where we are here. Don't worry so much about all this stuff that's in here. It's kind of like, whatever, blah, 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 blah. Here's what you need to know. Sound waves, a series of condensed, squeezed, and then spread out, rarefacted molecules. That's what sound waves are. Put a star by that. Okay? Then we're going to the next point. Do you see now how we're going to another kind of a section? Okay, once you've absorbed this section, now we move on to this section. And here you're looking at two types of waves. One's longitudinal, the other one's transverse. There's two kinds of waves in the world. Look, this type of wave is longitudinal. the one I'm circling here. When we draw it up and down like that, that's a transverse wave. Now, give me an example of a transverse wave. It could be water. Water waves coming at you. You're standing on the shore, and there's waves coming towards you. Well, the wave is going up and down, but its direction is coming toward you, right? So if I stop sharing and have a look, a wave, okay, it's going up and down, but its direction is coming toward you. So the up and down of the wave is perpendicular to the direction it's going. So the wave is coming toward you, but it's also going up and down. That's a transverse wave. Transverse waves are like water waves. Okay? Sound waves aren't. Sound waves are longitudinal waves. They're doing this. Okay, the squeezing and separating is happening parallel to the direction in which the sound wave is going. So that's, you're getting squeezing and separating, and that's moving in a direction. Water waves do this. And it's all to highlight that one point that I keep on mentioning, and that is this. Sound waves do not go up and down. We draw them like they go up and down. We draw them like transverse waves, but really they're longitudinal waves. Transverse, the up and down, is perpendicular to the direction in which the wave is traveling. And just in case someone's thinking, what the heck is perpendicular? I'll just, let's see, I'll just stop sharing here. Okay, if we're just in our, oh, I don't want that. Okay. All right. Okay, hang on here. Looking at here. And what I want to do. Okay, here we go. Okay, so, oh, I was probably, I'm not sure if I was sharing that or not. Anyway, perpendicular means like this. Okay, like a plus sign. The up and down motion is perpendicular to the direction of the wave. Okay, parallel means like that. So sound waves in air are truly longitudinal waves. Water waves actually do go up and down. That's the purpose of that next section in your notes. So now we look at the that section. That's this. Okay, so now you've absorbed that portion. So then we can move down to the bottom of page 1. Now this here, you can put along the side in your notes, right down in your margin, either over on the left or on the right. Write down the letters F, N, O. For nerds only, or freak not out. Okay, because I'm never going to ask you this stuff on a quiz or a midterm. It's for nerds only, or just to tell you, don't freak about it. Okay, FNO, freak not out, or for nerds only. What do I mean by that? Well, let's just show you what this bottom section is talking about. Okay, I'll just give you an idea really what it's talking about. So, okay, go to our kind of, it's this slide. You're looking at this slide here. You can see a circle on the left. And a circle has 360 degrees, right? You can do a 360 in the parking lot. Okay? So you're starting at 0 degrees, 90 degrees, 180 degrees, 270, back to 360. Now you're back where you started. If you look to the right, this is how you draw a sound wave. And can you see how the wave kind of gets pointed at the top and then kind of pointed at the bottom? In other words, it's not really round like in this picture. Okay? Notice how the blackened areas kind of are darkest right in the center, and the white is whitest right in the center, and the blackest right in the center. Here you got kind of gray, and then it's black, and then it's gray. Well, this wave here doesn't, if you were really showing a longitudinal wave in a true transverse way, you'd really be representing the top area. If drawn as a sound wave, it would really look more like this. This would be the black area, white area, okay? So they would be kind of pointed. That's all that that bottom third of page 1 is describing. So, look at the swing. Here, where 1 cycle equals 1 forward, back, and forth motion. Notice the speed is fastest right at the ground. It's when you get to the top that it's actually the slowest. And then wham, down across. So one thing you will often notice in your notes, put a star by this guy here. Sound waves are often referred to as sinusoids. Sinusoids. Because condensation and rarefaction are sinusoidal. What does that mean in English? Hey, your sinuses. You're behind your nose. The Latin word for curves is sinus. 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 Okay, your sinuses behind your nose that get infected with a cold or whatever, they're folds behind your nose. That's why they're called sinuses. Sound waves are also often called sinusoid because sound waves are curved. That's how we draw them. Okay, so when you're reading stuff about sound and you encounter the word sinusoid, all you have to think of, oh, that's just talking because sound waves are drawn like rounded. Okay, that's all. That's all it means. So never get confused when you see that in your notes. Okay, good. Share a screen again. I'll go back to our let's go down so we're done page 1. Let's scroll down here. There you go. Now there's 2 ways to represent sound, but before we even do that, let's look at the PowerPoint. Let's go back to the PowerPoint slides. Here you go. So we've done that here. I'm going to blow this one up bigger so you can see it more better. Okay? Here's a speaker on the top, and it's producing a rarefaction, a condensation, a rarefaction, condensation of molecules, and we draw it like this, right? And look at this speaker here. It's making a condensation, a rarefaction, a condensation, a rarefaction. And you draw that sound wave like this. So every time you're up, it's the dark areas. Every time you're down, it's the white areas. So what's the difference between these 2 sound waves? The difference is the top one has a lower frequency. The bottom one has a higher frequency. There's more bumps in the bottom one than there is on the top one. So now look at what the arrows are telling you. This is time along the horizontal. You could call that a second. Pretend this is 1 second. From here to here is 1 second. How many bumps do you see on the bottom? I see 4. So that would be 4 cycles per second. What's a cycle? Look where I'm starting. 0 degrees to 90 to 180 to 270 to 360. Now I'm back where I started again, right? So then 0 to 90 to 180 to 270 to 360. Now I'm back where I started again, and so on. So how many cycles do we see? What's a cycle? 1 condensation, 1 rarefaction. So here, 1 condensation, 1 rarefaction. 1 cycle, 1 black, 1 white. 1 black, 1 white. Okay? So as it's shown here, 1 cycle here, a second cycle here. Okay, so 1 condensation and 1 rarefaction is called a cycle of sound. 1 rarefaction, 1 condensation is a cycle of sound. 1 condensation, 1 rarefaction is a cycle of sound. And you can see it here. 1 condensation, 1 rarefaction. Now I'm back where I started. That's 1 cycle. By the way, if I took this, look where I'm circling here, and I swung it around under here, I'd have a circle. See, 360 degrees. Just like a circle has 360 degrees, so does a cycle of sound. All I did was take the bottom of the circle and flipped it over here. Okay? So that's how to understand a cycle of sound. So the top wave, if this is 1 second, it's got only 2 bumps. So it's got 2 cycles. Actually, let's kind of from the bottom to the bottom, okay, and that's 1 cycle. It's got like 1.5. Let's do this one. 1 cycle, 2 cycles, 3 cycles, and a half. So I guess this is 3.5 cycles. This is 1.5 cycles. Okay? There you go. Don't worry about that slide. So here you're looking at 1 single cycle of sound. And what you can see is the 0 degrees, 90 degrees, 180, 270, and 360. This is the condensation, the squeezing of molecules. This is the separation, the rarefaction of molecules. Look at this. Sine wave. See, sinusoid, sine. Just means it's got bends. Showing a sine wave into 360 degrees. And always realize that the horizontal is time, and you usually call it a second. And the vertical is the height. How tall is the wave? And that's amplitude. So if we went to this sound here and made it really loud, the black would be really black and the white would be really white. There would be less gray area, okay? And same here. Made it louder, the amplitude would be taller and the valley would be deeper. The height of the wave is the amplitude, and the number of waves per second is the frequency. And let's break down that word frequency, because we use frequency with everything. What's the frequency of your footsteps? What's the frequency of a radio station? The frequency is how many times something happens per second, or per any unit of time. Usually choose a second. How many times does something happen? How many footsteps per second? What's the frequency of your footsteps while you're walking? What's the frequency of your footsteps while you're running? Okay? Frequency is the number of times something happens per unit of time. And in sound waves, the number of cycles per second is called the frequency. You can have a low frequency, which means a bass sound, or you can have a high frequency, a bird sound. Beep, 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 beep. All right, so here we go. This would be a low frequency tuning fork. And this one might be a high frequency. I don't know if you can even hear it. Okay, a high frequency, low, middle, high, bass, treble. Bass is low frequency. There's fewer cycles per second. And a bird chirping, or the crickets, high frequencies. Now, before we even go anywhere else, I'm just going to talk to you about what this all means in what you're learning about hearing aids. What's the most important sound that a hearing impaired person wants to hear? It's speech, people talking. And when you think about the word speech, our speech has low frequency sounds in it, and it has high frequency sounds in it. The low frequency sounds of speech are coming from your throat. Ooh, E. All your vowels, A, E, I, O, U, Y. If you put your fingers to your throat, all those sounds are louder and lower. They're louder and lower. But now make the letter S. Hold your hand to your throat and say, S. Didn't vibrate, did it? Say the letter K. Didn't vibrate, did it? Say the letter T. Say the letter CH. Didn't vibrate. Those are called consonants. The consonants of speech, all the lip sounds that you make, are high-pitched. Vowels come from your throat. They're low-pitched. They're low frequency. And guess what elderly people have? Treble hearing loss. They have trouble hearing treble. So they can hear low pitch, they can hear low frequencies, they can't hear high frequencies. So they've got trouble hearing treble. And when you have trouble hearing treble, you can't tell what the person said. Did they say dishes or fishes? Think about this. I'll cover my face. Fat, cat, hat, bat, sat. They all have ah, ah, ah. What makes them different is the k, and those are treble. And elderly people can't hear treble. So they have trouble hearing what young people are saying. They say, oh, you young people mumble today. Okay, that's why they say that. So this is all tied together. What you're learning here in this course is what sound waves are. But I'm always going to tie it together with speech. And I always want this course to make sense to you in terms of the whole context of what you're going to be learning in this program. There's two really, really important courses that are fundamental pillars in the HIS Hearing Instrument Sciences program. One is this course, Acoustics. The other one's the one we're going to be talking about in a couple hours from now, Anatomy, 120. 110 and 120. Those are the two legs upon which the whole program stands. So I really want to encourage people taking this course to make sure you really internalize the concepts. I'm always going to try to make it make sense to you. I never want to be one of these people that's just giving all kinds of detailed, weird scientific information and you're sitting there trying to memorize it for what? I want it to make sense. Okay, so now we'll go back to our notes because we're 45 minutes into this course. We only got about another 15 minutes to go. See how time flies when you're having fun. I'll start sharing screen here and let's look at the notes, or let's look at the PowerPoint slide here. Okay, there you go. Here's another sine wave. Now this sine wave began at 0 phase and went to 90. Look at this one. This one began at 0 and went down here. Doesn't mean it's not a nice person or a nice sound wave. It's just a different phase. Look, if I go to the speaker, this one's beginning at rarefacted phase. Look, see, it's, the down is the first part. The black is next, so the up is the next part. Whereas this bottom wave here, this one began as a condensed. And so the up came first, and then the white came later, so the down came next. Okay, so these two sounds are not only different in frequency, they're also different in phase. When did they begin? All right, so there's 3 dimensions to sound. The amplitude, in other words, the intensity, the loudness, the frequency, the number of cycles per second, in other words, and thirdly, the phase. So here is a sound that began in this phase. This sound began over here, okay? If this is 1 second, and this is 1 second, you have 1 cycle happening here, you got 1 cycle happening here. This one started with a rarefacted and ended with a condensed. This one started with a condensed and ended with a rarefacted. Either way, they're both 1 cycle because they both have 1 condensation phase or piece and 1 rarefacted. Together they make 1 cycle. There's 1 cycle here and 1 cycle here. There's also 1 cycle here. Because if I started here and go now, I'm all of a sudden back to where I started from. So this also has 360 degrees. This one has 360 degrees. This one has 360 degrees. Okay? As long as you're ending up where you started, you've gone through 1 cycle. As long as you're ending up where you started. As long as you're ending up where you started, you've gone 360 degrees. So here's a sinusoid or a sound wave that began at 90 degrees starting phase. Just doesn't matter, okay? So now we're looking at a picture that talks about the 3 dimensions of sound. The 3 dimensions of sound. The top one, the middle one, the bottom one. Here, look at the top. 2 tones with the same starting phase and the same amplitude. They're the same height, but they've got different frequencies. This one here has more bumps. This one here has fewer bumps, but they're the same height, so they were equally loud, they were equally intense, And they're both starting at 0 degrees phase. Okay, so what's different here is the frequency. If you look at the middle two sounds, they're the same frequency. You got the same amount of bumps, and they're the same amplitude. They're just starting out at slightly different phases. And if you look at the bottom pair of sounds, they're starting at the same phase, and there's the same bump, but one smaller than the other. But the frequency is the same. The number of bumps per second is the same. So what's different in the bottom pair of sound is only the amplitude. The phase is the same, the frequency is the same. So remember, there's 3 dimensions to sound: amplitude, frequency, and phase. Here it is shown again. Okay, here's a top pair of sound, a middle pair of sound waves, and a bottom pair. In the top pair, the frequency is the same. If you call this 1 second, from the left to the right, call that 1 second. What's the frequency here? Well, let's count the bumps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 10 cycles. How about here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you've got 10 cycles per second. So the frequency is the same. They're both starting at the same phase. So what's different? The amplitude. Look at the middle pair. The middle pair are the same height. They're mainly differing in frequency. And the bottom pair is the same height, the same frequency. They're just in opposite phase. Now, if you played the bottom 2 sounds together, you'd have the sound of one hand clapping. They'd cancel each other out, wouldn't they? Totally, flat line. So anyway, just thought I'd tell you that. Now, before we go here, let's escape out of here. Let's go to our notes and make sure we're all there. Look at where I'm highlighting. Okay? Note the different amplitudes, the top panel of the slide I just showed you, the frequencies, the middle panel. Note the different phases in the bottom panel of the slide I just showed you. Those 2 tones were 180 degrees out of phase. They'd cancel each other out. Silence. Here, read with me right here. Tones that are presented in phase would reinforce each other and increase the amplitude. Okay? A pure tone is a simple sound with a single sine wave. These are relatively quite rare. Most sounds are complex. They mean there's many different frequencies happening together. If I'm showing you a single sinusoid, if I'm showing you a picture like this, that's just showing you one particular sound wave. You're showing several sound waves here. Here's a sound wave, here's a sound wave, here's a sound wave. Big hairy deal. Most sounds are combinations of many different sound waves together. Think of traffic, noises, music, speech, all kinds, door slams. They're all different kinds of sounds. And so those sounds really are what we call complex. They're comprised of many different tones together. Noise, voices, music. Hey, you'd think I wrote these notes. Yeah. All right. Over here at the very top, there are 2 ways to represent sound. And we'll slowly kind of finish with this section here. Okay? If I go to the PowerPoint slides, I'll see if I can't show you. So the one way we've described sound is in sound waves. We've described that one already. What's the second way that you can describe sound, or what do you call pictorialized sound? It is called a spectrum. There's a picture of a spectrum. And this picture is showing you this cycle here has 100 cycles per second. This sound wave has 200 cycles per second. This sound wave has 300 cycles per second. So on a spectrum, it shows you frequency along the horizontal axis and amplitude on the vertical. Whereas a sound waves, it's time on the horizontal and amplitude on the vertical. In both ways, amplitude is on the vertical. Okay? Amplitude is shown here. Time is shown here on a spectrum. Amplitude is again shown on the vertical, but this time frequency is shown on the horizontal. Why am I showing you this? Because remember we said sound waves have 3 dimensions: frequency, intensity, and time. And yet a piece of paper only has 2 dimensions, length and width. So how can we combine all 3 dimensions of sound on a piece of paper? It's only by showing you a spectrum, which shows you frequency and intensity, and a sound wave, which shows you time and intensity. Either way, now we've been able to show all 3 dimensions of sound. Let's see. I'll go out of here into the notes. And the last thing, our parting words today are going to be about frequency and period. Right there. And I'm going to make it bigger so you see it even more better. So I'll move it over here so you really highlight it. Read with me. Frequency, the number of times something happens per some unit of time. For sound, frequency refers to the number of cycles per second. And we call that hertz. Is in what used to be Hertz Rent-A-Car. Okay, hertz. H, capital H, E-R-T-Z. It's always capital H, little z. 1 hertz equals 1 cycle per second. 1 cycle. So a sound with a frequency of 100 hertz or 100 cycles per second is called 100 hertz. Okay? Very important. Hertz. Capital H, little z represents cycles. How many cycles per second is the hertz? If you have 100 cycles per second, and think of a sound that might have that. I mean, yikes, look at this guy here on the right. Whole bunch of cycles. Okay, if this was 1 second, you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like that. Yeah, that would be 11 hertz. This one here would be 1, 2, 3 hertz. This one here would be 1 hertz. Okay, it really hurts. The next thing is called period. Period is the time it took to complete a cycle. If a sound is 1 hertz, it took 1 second to have 1 complete condensation and 1 complete rarefaction. So 1 cycle per second is 1 hertz. What's the period? How long in time did it take for that cycle to occur? 1 second. If a sound is 100 hertz, then its period is 1/100th of a second. Do you see the point here? Then it would take 1/100th of a second to have 1 complete cycle, because you have 100 cycles in a second. So how long did it take to have 1 cycle? 1/100th of a second. So this is how we part ways today. Okay? Frequency and period are inversely related. As the frequency goes up, as the hertz goes up, the period goes down. So here we say frequency is 1 over the period. Period is 1 divided by the frequency. They are inversely related. The higher the frequency, the shorter the period. The more cycles per second, the shorter the time to complete 1 cycle. We'll continue on this one next week. I'll stop sharing here, but this is where we will begin next week. We'll talk about hertz, frequency, and period. And then we'll start to move into wavelength. How long is the sound wave? How many feet long is it? How many inches long is it? Now, I'll tell you something, just sort of as a tease to you Americans living down there in Missouri and where else in the States, okay? You guys are talking feet and inches. The rest of the world has gone metric. So the rest of the world doesn't talk about miles an hour. We talk about kilometers an hour. We don't talk about yards. We talk about meters. But Canada's kind of halfway like Europe, halfway like US. So we still use feet and inches, but we also use metric. Okay? We talk about miles per hour, but we also talk about kilometers an hour. We talk about inches, but we also talk about centimeters. We're a bit of a mix. We haven't made up our minds yet. We do a bit of both. Let me ask you guys, where are you from? Alyssa Long, Grace Patton, Sibby. I see the names on my screens. I have no idea where you're from, but I see a chat. I do see one chat. I see something highlighted here, like a chat. I gotta look at that. What is it? Where are the notes located at in Canvas? Oh, when you go on the unit, when you click in the unit, when you go onto the course, you go onto what they call the dashboard, and you look for 110.19. You look for the number 19 because that means 2019. And you click on that particular thing in the dashboard on Canvas, and the course will open up. And when it opens up, you're going to see units, 1, 2, 3, 4 on the top, 5, 6, 7, 8, like balls, like round circles. Click on Unit 1. And when that opens up, then scroll down and look, and you'll see a blue link for for notes, and a red one for the PowerPoints. That's where they're located. Okay? And have a look at the email that I just sent you. Oh, you're Sibby's from Rogersville, Missouri. Okay, cool. I'll look at a map and figure out where Rogersville is. I'm not from Missouri, so I kind of have a view of the state. I know where St. Louis is, and I know where Springfield and Kansas City are, and Joplin and Columbia. I have an idea, Rolla. So I know your state somewhat, but I don't know where Rogersville is, but I'll take a look there. Okay, so you are from in-state. So you're not from too far, I imagine, away from the school. Anyway, it's now 10:31 where I live. It's 12:30 Central Time. We're basically done here. It's all good. So I'm going to stop recording the session, and then I will upload it later this afternoon as a YouTube, and that will also be found on the unit. Okay, so you'll see the notes, the PowerPoint, and later on this afternoon you're going to see the YouTube itself. That is taking me to the home page. I still don't see the notes, says Alyssa. It's taking me to the home page. Still don't see the notes. Not sure. That one, maybe you better ask Lynn Royer or Rebecca Krause. But they are in there. If you click on the unit and then scroll down, you'll see it plain as day. This could be just something we are kind of doing a little bit wrong here. But basically, you go into the dashboard. You click on the course opens up, you'll see 8 units, click on Unit 1, and there it is. You'll see it clear as day. All right, I'm going to stop recording here, and we'll say adieu, live long and prosper. We'll see you next week. All right, and Alyssa, having problems finding it, do talk to Rebecca Krause. She's excellent at knowing all totally around Canvas. Me, I'm living 1,000 miles away from you. I know how I access it. I try and explain it as best I can from my end, but check that out. Be sure, though, to look at the note and then watch this session the second time. All right. Adios, amigos. Stop recording.